There we are. Bit of maths. Bit of maths. Why at school do teachers keep what you're trying to learn a secret? Why do they do it? If they want to teach you a 10 times table, why don't they put that on the wall behind them? And they say, now what's 9 nines? You can work out 9 nines, 9 across, 9 across, and 81. Got it. But don't you see, you've got to say to the kids, there's no mystery in this. When asking you to do something that's never been done before, so you find fascinating things. You know how the arrows used to teach numbers? It's quite simple. It's incredibly simple. They used to, you know, and you can do this before preschool. Preschool you can do this. You give a kiddie a counter and say, put one down. And there's a counter, perhaps a blue one or a black one, right? Now there's one across that way, there's one down that way. They say, now, here's 3 yellow ones. Can you make a square? And the kiddie would go, oh, make a square. You know a square. And perhaps do it for them if they're very young. And you say, how many have you added? They go, oh, 3. All right. So what's that? Give 2 there and 2 there. 2 twos is 4. Oh, thank you. Now let's take some blue ones or something like that and make another square. And the kiddie will say, so how many are you going to need? You've got to put 1 here, yeah. Another one where? Yeah, all right. Then there, then there, then there. And you've got another square. And you've added 1, 2, 3, 4, 5. And what have you got? 3 threes, 9. And suddenly the child is realising very quickly that if you take the odd numbers and keep adding them, you always get squares. 1 plus 3 is 4, plus 5 is 9, plus 7 is 16, plus 9 is 25, plus 11 is 36, plus 13 is 49. And suddenly you're teaching a child at preschool a rule of squares. And it's incredibly powerful. I'll show you more squares later on. And they're the squares. They go down in a diagonal line. And then you say, so 6 sixes is 36. So let's go one each way. Not 6 sixes, but 5 sevens. What's that? 1 less. Always 1 less. 7 sevens are 49. What's 6 times 8? 1 less. 48. And there they are, each side. And suddenly you're teaching them basic algebra. Understanding x squared plus, or x plus 1 times x minus 1. And suddenly it's all there. And if that is there, suddenly they realise at the end they'll learn it. And you can. 1, 2 is 2, 2, 2 is 4, 3, 3 is 6, 1, 5 is 5, 2, 5 is 10. It's all there. And then start hiding it later. But not hide it from the start. And not teach the 5 times table in in 1 year and say, oh, you can't learn 6 times 6 till next year. That is potty. A lady called Maria Montessori was the student of the year in Italy about 1904. And to celebrate, no girl had ever won this accolade. And to celebrate, they gave her kids to teach. And the kids were all disabled and malnourished and in a terrible state in some kind of hole. In 3 years, she had them passing the exams for their age, every single one of them, irrespective of their assumed difficulties. And she said, so why do other kids, normal kids, healthy kids, why do they fail? She couldn't understand it at all. And you need people like this to improve. What have we got? We've got all kinds of people who form a curriculum that gets less and less and less, and it's a tragedy. It is. I'll show you how easy it is to multiply. 2 volunteers. Now, it's always a mistake to sit in the front row. One of them must be very tall. One of them must have upset people by having his mobile phone on. Would you come up, please, sir? Would you come up, please, and bring one of the lads? Anyone you like. Oh, your legs are good. All right. He'll do. You there. You're a perfect position. Come up. Do you want to bring one of his lads? You okay? Here he comes. Give him a round of applause. Here they come. You're a lovely audience. You're a younger audience than I anticipated, so the material I'm using is a bit different. You come over here, young man in the green, and hold that ring. It might be the right way up, it might not. Don't know. You, sir, if you come in here and hold. Now hold that one back there. Oh. Yeah, and this one. About there, I think. As long as I know what I'm doing. Yeah, thank you very much. Right. Now, A man called Eratosthenes, 200 BC. He said, why do people hate multiplying? Why do they hate maths? I can't understand it. Why do they hate it? Pick your teeth up. You're right. Why do they hate maths? It's so simple. All you need is 2 lines. Do this with the kids at home. Get your teachers to do it at school. Draw 2 lines. The angle doesn't matter as long as it's up here. It can be any angle you like. That's why I've chosen the chapter, not going to make it right. And with this, on 2 rulers, you can multiply or divide any 2 numbers. So say you want to multiply 3 times 4. Do you know the answer? 12, thank you very much. But we're going to find it. 3 times 4. You count 1, 2, 3 on that man, and 1 on that man. And then you draw lines with the 1 and the 3. Picture of 1, 3. You can't miss it. It's a picture of 1, 3. You want 4 3s. You put a parallel line through that one. And that top line, if it's parallel, should go through the 3, 6, 9, 12. Have I done it? 3, 6, 9, 12. It works. It works perfectly on paper. Not only that, the second line is exactly 4 times longer than the first line. And parallel lines gives you 1 3 is 3, 2 3s is 6, twice as long, 3 3s are 9, 3 times is 1, 3 and a half 3s is 10 and a half. And it's easy. Division, 12 divided by 4, line to the 12, line to the 4, parallel line to the 1, give the answer 3. 12 divided by 4 is 3. Couldn't be simpler, could it? Galileo discovered this. He liked it so much, he engraved it on little copper or brass, I'm not sure which, and he had a chain, and added to that were 2 sticks, very small, only about that big. But the sticks were hinged so that they opened and stayed parallel. You can imagine parallelograms, sort of thing, you can imagine that. And he sold 7. So he didn't catch on. But a man called René Descartes found this. And found it not only worked, but it doesn't matter even if they're not the same rulers. This ruler could be going up in 7s. 1 7 7, 2 7 14, 3 7 21, 4 7 28. Still work. And then he realised that the angle doesn't matter, the angle could even be up there. And then he had these lines going like that. And then he thought, hang on, Cartesian coordinates. And he found a way of producing maths where every spot can be divided so far across and so far up or down. And in 3 dimensions, so far in. And today we have computers. And on a computer today, you can design a film like Jurassic Park. You can design computer games where the stuff really comes at you. We're now doing 3-dimensional film using the same thing. It's the same maths that René Descartes laid down. So you see, when you invent something, it's never perfect. But as we go on, we perfect it, and we're getting better and better. But it's the old ideas that are incredible. Now, this is for the older ones, so I'm going to show you, the kids as well. This is incredible. René Descartes wrote a book called The Geometry, and The Geometry was just as much a cause of the Industrial Revolution as the steam engine. Because The Geometry taught you how to measure anything. And so it's used in art, graphic design, designing engines and things like that. All these ideas that he had. And at the beginning of the book, he had the one I just showed you, with the parallel lines. And he also said, and I'll show you how to find the square root of any number with a ruler and a pair of compasses. So say you want the square root of 9. Do you know the square root of 9? 3, thank you very much. Some people get very nervous up here. Sometimes they go, oh, when they know really, but you're all right. So, we're going to find the square root of 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. You count 9 along a ruler. Then you add 1. Why? Because that's what makes it work. So you've got 10. What's the halfway point of 10? 1, 2, 3, 4, 5. So with 5 as centre and 5 as radius, you produce an arc. You can produce a whole circle, which will pass through there and the 10. But all you need is the arc. And you raise a perpendicular from there. And whenever that line meets that curve, that distance is always exactly the square root of that. For any number. It's as simple as that. And that coded, put into a program, is what makes your square root key work on your calculator. Do we teach our kids this? Why? Too easy. Okay, so there you go. Give these 2 a round of applause. Thank you very much. I do lots of different talks, and there's lots of material, and I can jump one to the other. Because it's a nice young audience, I keep it young, so I'm actually not going fast enough today. I'm not going fast enough. Now, this should work. Oh! I read a book about the Great Pyramid of Giza. This was when I was 17, and I thought, I've got to read I've got to read. I had no education, not even in the sixth form. I've got to educate myself. And this is one of the first things I found. This was the most incredible thing. The Great Pyramid of Giza is still arguably the heaviest building in the world. There are skyscrapers much bigger, but they actually get lighter these days with their modern materials. And what is a building? A building is a collection of spaces. It's all right looking at the outside of the building, isn't it good? If the space inside out, well, this is a beautiful hall. It's a beautiful hall. And that's what a building is, a collection of spaces. No spaces. Just a couple of corridors and one room, another little room. That's it. The rest is all solid stone. How much stone? Enough stone in the Great Pyramid to build a brick wall 2 meters high, 18 centimeters wide, about that. And you can build a wall that thick, that high, with the stone in the Great Pyramid that will go from Egypt, where the pyramid is, and that wall will stretch to the North Pole. One building. The stone, isn't it incredible? But who built it? People who love maths. And why was that? Because of the shape. And I looked at the shape, and the shape is incredible. Why not a taller building? Why not a shallower one? They chose the only shape. We would take the height, turn it into a radius and form a circle. The distance around the circle will be 922 meters from the original height. The top's missing, but the original height.